Our final speaker for today's session, for plenary session, is Elizabeth Turtle, the principal investigator of NASA's Dragonfly mission to Saturn's largest moon, Titan.
So I'm Zibby Turtle. I'm a planetary scientist at the Johns Hopkins Applied Physics Laboratory, and I'm the principal investigator of the Dragonfly New Frontiers mission to Titan. And I'm really happy to be here today to move a little further out in the solar system and to talk about Titan and Dragonfly and what we're going to do there. As those who have explored Earth and Mars know well, for planetary exploration, the ability to travel through, within, and to interact with the environment is immensely beneficial. And most in situ exploration to date has been in the form of driving, but we're starting to look to the skies of other planets as well, as Ingenuity has demonstrated really beautifully. There are, of course, many benefits to being able to fly rather than to drive. And for Saturn's moon Titan, this is especially true. Titan is a unique moon in that it has a dense atmosphere. It's actually 4 times the density of Earth's atmosphere. And that, combined with the low gravity, which is about 1/7 that of Earth's, make it an ideal place to fly. All other things being equal, it's physically easier to fly on Titan than it is here on Earth. And for that reason, the Dragonfly New Frontiers mission is a rotorcraft lander. So it's technically an X-8 octocopter. It has 4 arms and 4 pairs of rotors. And similar to the Mars rovers, Dragonfly is a single self-contained vehicle that carries its entire payload of science instruments from place to place. Now, at Titan, we don't have the same infrastructure we have at Mars, with orbiters that can serve as relays, etc. So Dragonfly communicates to Earth directly from the surface with the high-gain antenna you can see here, which we have to stow during flight, because unlike most spacecraft, we actually have to consider aerodynamics as well. So of course, the work I'm presenting here reflects the efforts of a very large team of people who have been working incredibly hard and making great progress on our design, the design of the mission, on the technology maturation, etc., despite the complicated conditions that we're all working under during the COVID pandemic, working remotely, as you see here in the picture of our team meeting. But we're all just thrilled to be able to continue to make progress toward exploring Titan. So I'll start by giving an overview of Titan itself, and then I'll talk about what we want to learn there and our plans to explore Titan with Dragonfly. So first of all, why Titan? We don't know how life came to form here on Earth, and we can't go back to study our prebiotic history. It's kind of overprinted by biology. So we looked to places elsewhere in the solar system, of course, to provide pieces of the puzzle. And Titan, in many ways, is most like the early Earth chemically. And so it holds keys to understanding our chemical origins. So Titan is the largest of Saturn's 62 moons. It's shown here with some of its siblings. It stands out because not only is it large, but at visible wavelengths, it's very difficult to see the surface because the atmosphere is very hazy. And this is Titan just for comparison to other bodies in the solar system. So Titan's between Mars and Mercury in size, but its atmosphere is, as I mentioned, denser than Earth. So it's actually the second densest atmosphere of the bodies with solid surfaces in the solar system. Titan's actually the second largest moon in the solar system. It's with a diameter a little over 5,000 kilometers. It's just a bit smaller than Jupiter's Ganymede. The surface temperature out at Saturn's orbit is cold. It's 94 Kelvin, and at these temperatures, the bedrock composition is water ice. And the atmospheric composition, like our Earth's, is actually mostly nitrogen, but the next major constituent is methane. And that's where things get really interesting, and I'll talk about that in a little bit. As I mentioned, the surface pressure is about 1.5 times that here on Earth, or the density is 4 times, the surface pressure is 1.5 times. And then deep underneath the ice shell, there's actually a liquid water ocean, similar to many of the moons in the outer solar system. So The methane in Titan's atmosphere undergoes photochemistry at the top of the atmosphere, and the molecules recombine to form very complex carbon molecules. And these molecules aggregate as they descend down through the atmosphere into aerosols, and this material falls out onto the surface. So we have this very rich organic material that covers the surface, and the surface of a moon made of water ice means that there's the potential for these organic materials to have mixed with liquid water at the surface. Not most of the time, the surface is frozen solid, but at the sites, for example, of an impact crater, or if there is cryovolcanic activity, there's the opportunity for organics to mix with liquid water, possibly for extended periods of time. And so this is what makes Titan such a unique destination, to understand chemical processes that may be like those that occurred on the early Earth, supporting the development of life. So for those who aren't familiar with Titan, for an icy moon in the outer solar system, its geology is surprisingly familiar, with similar surface processes to those we see on Earth or Mars. And this is a map at infrared wavelengths with enhanced color, made by the Cassini orbiter. Cassini was in orbit around Saturn for 13 years, and it mapped out the surface of Titan at a variety of wavelengths, including radar wavelengths and this near infrared mapping. So Titan doesn't immediately look familiar when one looks at it. There are a few impact craters you can see, but there are not many. And there are these big dark areas near the equator, and there are very large dark areas near the North Pole. And I'll talk a little bit about each of these. So it turns out that these dark areas near Titan's equator are fields of dunes, sand dunes, except on Titan, the sand is made of organic material. We don't actually know how you form organic sand grains. We'd like to find out. But Titan basically has the equatorial region is basically the largest Zen gardens in the solar system, with these spectacular longitudinal dunes. And this area wraps almost all the way around the planet. Titan, as I mentioned, does have a few impact craters, but like Earth, it doesn't have very many. And that is mostly due to the fact that there are active processes modifying Titan's surface the same way we have here on Earth. And so they're eroding craters and depositing material in them to the point that the craters become unrecognizable. There are also some tectonic structures you can see, and I should explain, this is a radar image. So the features that are bright here are features that are rough at the wavelength of the radar, which is about 2 centimeters, 2.2 centimeters with Cassini's radar wavelength. So what you're seeing here is these bright areas. These are actually elevated tectonic structures. They're actually fairly eroded because there's so many other processes modifying the surface of Titan. And you can see these dark linear features, which again are the organic sand dunes. There's also the possibility of cryovolcanism. This is one particular example called Sotra Patera, which is almost 2 kilometers deep, right next to this mountain. It's 1.5 kilometers high, and when one looks in the radar and infrared data, one can see features that look like flow features on the surface. So we didn't see anything that was active cryovolcanism with Cassini observations, but there are certainly hints that there may have been cryovolcanic activity in the past. And then Titan also has a hydrologic cycle. So Titan has channels, and in fact, at the North Pole, the areas that you see as dark in the map are these large seas. There are 3 large seas here. Ligeia Mare is 500 kilometers across. And then all these little dark features here on the other side of the North Pole, which is about here, are lakes. And these are lakes and seas of liquid methane. There are rivers of liquid methane, and there are even clouds of methane in the atmosphere. And Cassini saw evidence of methane rainfall a few times during its mission. So Titan actually is a world kind of 2 oceans, in that there are these methane seas on the surface, and then there's a liquid water ocean in its interior. Cassini carried with it a Huygens probe built by the European Space Agency, and it made measurements as it descended down through Titan's atmosphere and sent us back this view of Titan's surface. And of course, the view right next to it is a little more familiar, of our moon, just to give a sense of scale. And what you see are these this gravelly plain with rounded rocks that are probably made of water ice, extending off into the distance. So we know that Titan has the key ingredients necessary to be necessary for life. There's energy in the form of sunlight that drives this very complex and rich photochemistry. There's the organic material that is the result of those chemical processes. This material falls out, covers the surface, where it's had the opportunity to mix with liquid water in the past, or perhaps in the present day, if there's exchange between the surface and Titan's interior liquid water ocean. But there's also a second liquid in the system, which is the methane and the active. It's possible that liquid methane could support the development of an exotic biological system. And on Titan, we can study the chemical processes in the context of a planetary environment that's very much like, the processes that materials are exposed to here on Earth. So Titan offers us the opportunity to look for answers to very fundamental questions. What makes a planet, or in this case a moon, habitable? What are the chemical processes that led to the development of life? And even, has life developed elsewhere in our solar system? So of course, we don't think that life as we know it certainly would be terribly happy at 94 Kelvin, but we would be remiss if we didn't make measurements to understand if chemistry did was able to take the step to biology at some point in Titan's past. So Titan has basically been doing chemistry experiments, prebiotic chemistry experiments for us for tens of millions, hundreds of millions of years. And Cassini has shown us where we want to go on Titan to pick up the results of those chemistry experiments. We know that there are diverse surface materials and environments. There's this wide variety of geologic processes, transporting and modifying materials on the surface and mixing them together. So the challenge became, how do we get instruments to multiple sites to be able to sample materials and measure the compositions of these materials? Very similar to the challenges that the rovers on Mars are surmounting in making these measurements with mobile in situ exploration. But as I mentioned, it's very efficient on Titan to travel using heavier than air flight. And so that's exactly what we plan to do. So the Dragonfly mission, actually, we have a cruise stage that will get us from Earth to Titan. And then we have a entry vehicle that protects Dragonfly as we descend down through the atmosphere to Titan's surface. And then there is the lander itself, which, as I mentioned, is an entirely self-contained vehicle. It carries our entire payload from place to place the same way we do on Mars. But with Dragonfly, we can make measurements not only on the surface, but also in flight, doing aerial imaging and atmospheric profiles, for example. I also mentioned we do direct-to-Earth communication. We have the high-gain antenna that allows us to communicate. We take advantage of the fact that the antenna needs to be able to turn to communicate with Earth from the surface, and we mount these two cameras here. These two boxes here at the top of the high-gain antenna are actually cameras, and this will allow us to pan these cameras around to build up panoramic views of the terrain surrounding the lander. Dragonfly is designed like Curiosity and Perseverance. It's designed to use an MMRTG for a power source, and we use this to charge a battery that we use to power flight and our science activities. And what is typically referred to as waste heat is actually a significant element in our thermal design, because this allows us to keep everything inside the lander warm in the cold Titan environment. And just for scale, because we tend to think of drones as fairly small things that we can fly around in the backyard, the Dragonfly lander is about the same size as the Curiosity or Perseverance rover. And so this is a prototype. This is a prototype rotor, and I know you don't know how large I am, how tall I am, but I'm a pretty average human being, maybe a little short for a stormtrooper. Anyway, this is me with one of the rotors. So just to give a sense of the scale of this vehicle, it really kind of gives you a sense also of how much easier physically it is to fly in the Titan environment, that we can fly a Perseverance-sized rover from place to place. So Dragonfly is scheduled to launch in 2027 and to arrive at Titan by 2034. We do direct atmospheric entry. We go straight into Titan, no going into orbit around Saturn or Titan. And Titan's atmosphere is very extended. So at Mars, we're used to talking about the 7 minutes of terror. For Titan, the atmosphere goes up to, well, to over 1,000 kilometers altitude. And so this is a 2-hour descent. So there's a lot more time to kind of stage all those activities that when one is approaching Mars have to all happen in a very short period of time. But at Titan, we have 2 hours for this sequence to take place. We'll actually be landing at a similar latitude and similar time of year, of Titan's year, as the Huygens probe. And so we know what the atmosphere is like at this time of year in these areas. The initial landing site provides access to a wide variety of materials. We're going to land within the sand dunes, these organic sediments, to make measurements of their composition. The interdune areas between the dunes actually have a water ice component. So within very close proximity, we have 2 different materials with very different histories. And then the landing ellipse is just south of this impact crater. This is the Selk impact crater. It's about 80 kilometers in diameter. And we will explore this area, which will allow us to study an area where organics may have been able to mix with liquid water impact melt. Another benefit of landing in the interdune areas, these are terrestrial analogs. This is the Namib Desert. It's a very good analog for these longitudinal dunes that we have on Titan. Both of these pictures, though, of course, are taken on Earth. In addition to the fact that there are 2 different materials on Titan in the sand dunes themselves and the interdune areas, the interdunes form these very wide flat areas, which are ideal for landing as well. So there's a practical reason for landing in this area as well. And then it gives us access to the deposits associated with this impact crater. So Dragonfly exploration is planned for a little over 3 years, or 74 TSOLs, 74 Titan days, over which we'll traverse up to 180 kilometers, exploring a couple of dozen unique sites along the way as we go through the dunes and interdunes, and then into the deposits associated with the impact crater, and possibly down into the impact crater itself. I should say this is a very extended, a very vertically exaggerated profile here. The topography is really only on the order of a few hundred meters, and this is a 200-kilometer, x-axis. So like most icy satellites, the topography is very subdued. So at Titan, again, we don't have the same infrastructure we have at Mars. We don't have orbiters that can do scouting for us. So Dragonfly will actually scout for itself. We have global maps from Cassini, but those are at a lower resolution scale. And so Dragonfly will actually do what we call a leapfrog. What we call leapfrog flights. And so from a landing site, we'll take off, we'll fly past the previously scouted landing site, that is our target landing site, and go ahead and scout a new area, and then come back to the previously scouted landing site. And so this allows us to look ahead to areas where we want to go, to study, to not only look for hazards and do hazard assessment for safe landing sites, but also to look at the areas that offer the most scientifically. The nominal flight schedule is about once a Titan day. Titan days are 2 weeks long, about 16 Earth days long. So it's about 1 flight a month, which means that most of the time is actually spent on the surface making science measurements, transmitting data to Earth, etc. And we make multidisciplinary science measurements. The focus, of course, is the prebiotic chemistry. analyzing the composition of the surface materials, but we want to put that in the context of Titan's atmosphere, its methane cycle, the transport and mixing of organic material on the surface, and then the opportunities for the organics to mix with liquid reservoirs, be they liquid methane or liquid water. And then again, we have the capability to search for chemical biosignatures of water or hydrocarbon-based biological processes were they to occur or have occurred. And this is just a reminder for those who are more interested in more information about the science. There's a paper in the Planetary Science Journal that just came out this August by Barnes et al. And this is it summarizes the science that we're doing. So there's a lot more information there if people are interested. Dragonfly will carry with it a mass spectrometer. The DRAMS mass spectrometer built by Goddard is based on heritage from the SAM instrument that's on the surface of Mars right now. We have two drills, rotary percussive drills. This is the Draco system, or the drill for acquisition of complex organics. We use this to break up the surface. We use pneumatic transport to bring the materials into the mass spectrometer. Then we also have a suite of geophysics and meteorological sensors, including a seismometer to listen for Titan quakes, and to monitor the atmospheric conditions. We have a suite of 8 science cameras that look downward and forward, and I mentioned the 2 panorama cameras up here on the high gain antenna. And then we also have a gamma ray neutron spectrometer that will let us measure the bulk elemental composition for context of the surface area under the lander. So as I mentioned, the team's been really hard at work. We've been doing a lot of testing of hardware in the Titan environment, demonstrating the elements will survive in the Titan environment. And we've also been doing a lot of testing of the guidance algorithms and the control algorithms on some octocopter platforms. So I have a couple of little videos here, which I think I'll show if this works over the Zoom. And so this is one of our autopilot test flights, and what you're seeing on the right is the imaging from the navigation system that will be used to do optical navigation during Dragonfly flights. And another thing we're doing is getting other people involved in the project. We have a guest investigator program that is designed to expand opportunities to participate in missions, to get experience, even in these early stages of the mission, the design and development stages, by bringing in students who don't necessarily have experience or connections to Dragonfly or other missions, or may not even have a planetary science background, but to bring them in to give opportunities to really broaden participation, to build on-ramps and provide networking opportunities so that we can expand the training of a next generation of mission team members and leaders. So there's a lot going on. I know we don't have a lot of time. I will wrap up there, but I'll be happy to take questions as well. Thank you.
Wonderful. Thank you so much, Dr. Turtle. We do have a lot of questions. So let me start with one from Kaj. I understand Dragonfly's ceiling height will be as high as 13,000 feet. Will it make use of its ability to fly higher than the highest mountains of Titan? And if so, for what purpose?
So the mountains are pretty subdued compared to what we think of as mountains. Most of the mountains are only a kilometer or 2 high. And the area that we'll be flying in doesn't, besides the crater, there's not a lot of topography in that area. Mostly the reason we want to be able to fly a few kilometers up is to make measurements of the lower part of the atmosphere, to understand the atmospheric behavior. And how it changes with altitude. So we would be able to fly over, a mountain if it were there, but the intent of altitude profiles are really to understand the atmosphere better.
Thank you. Next question comes from Bernard Foying, and he asks, how far will you be from Huygens landing site? Any chance to investigate what happened to the Huygens lander?
It would be really interesting to go to the Huygens landing site, but it's actually several hundred kilometers away. So that is not part of the mission plan. The intent is to explore a different area of Titan and gain a sense of the diversity of the surface materials. But I agree, it'd be really fascinating.
Thank you. Next question is from Doug, and he asks, to date, our best sterilization of Mars landers sent less than 0.1% of Earth microbes. How will Dragonfly be sterilized so we can study prebiotic chemistry and a search for life?
So it's actually, so we do absolutely have to make sure that we know what we would carry with us and make sure we don't carry things with us that we would measure with the instruments. But on Titan, it's a somewhat different environment than Mars in that there is a lot of organic material. So the biggest challenge becomes making sure we're not cross-contaminating, that we don't get from, not that it's a problem for Titan because materials move around on the surface of Titan all the time, but to make sure that when we make compositional measurements at one site, and then make compositional measurements at the next site, that we're not, still measuring materials that were sampled the time before. So that's really what drives our contamination control requirement, is making sure that we're able to, the system stays clean between sampling sites. But absolutely, we need to pay attention to cleanliness all along the way as well, to make sure that what we're measuring on Titan is native to Titan in terms of the chemistry.
Wonderful. Thanks a lot. And as always, we have so many questions, but let me ask you the very last one from Dr. Zubrin. And he asks, what limits the lifetime of Dragonfly?
The lifetime limit is the output from the MMRTG, and not in terms of power so much as in terms of heat. Because as the output from the MMRTG declines, there will be less heat put into the Dragonfly system. And so the 3 years allows us to get from our initial landing site to the area around the crater that we want to study. The lifetime limit from the MMRTG is several years. Eventually there will be low enough power output, low enough heat output that Dragonfly won't be able to stay warm anymore. But that's several years, so we actually have a good amount of margin on our nominal mission lifetime.
Wonderful. Thank you so much, Dr. Turtle, for a great
My
presentation.
pleasure.